This is your College Chemistry 108. It's April 2nd, and we will continue on in Chapter 6, thermochemistry. Right, I remember now. So we finished last class looking at this table here, sign conventions for work and heat. We said when we're thinking about work and heat, remember the change in energy of a system, or what we call the internal energy of a system, depends on Q, which is heat, and W, which is work. And W, work, the most straightforward or the simplest form of work is what we're going to call P delta V work. It's expansion of a gas against a constant external pressure. Right? So if there's an external pressure and the gas is expanding, pushing it out, then work is being done. And then we started talking about the signs. And we started by looking at heat. Right? If heat is absorbed by the system from the surroundings, that's an endothermic process, right? We defined a whole bunch of terms. That's endothermic, and with respect to the system, the heat or the energy increases, right? So what does that mean? That means if we put a pot of water on the stove and we turn on the burner, energy is going from the burner, which is the surroundings, into the system, right? Which is the pot of water. And so from the point of view of the pot of water, the energy is increasing. And you know the energy is increasing because if you stick your finger into the pot, it's going to be hot. The opposite is if the heat is absorbed by the surroundings from the system. Or in other words, the system gives off heat to the surroundings. So from the point of view of the burner is giving off the heat. Right? So from the point of view of the burner, if the burner is the system, then the sign is negative because the heat is going from the burner into the pot and all the air that's all around. Okay, so that kind of is a little bit intuitive in terms of heat. Work, it's not quite as intuitive. So work done by the system on the surroundings, and work done on the system by the surroundings. Okay, so if work is done on the system by the surroundings, that means, well, let's start by the system, right? If the system is doing work, and if the system is doing something useful, if you and I do something useful, what happens to our energy? Our energy goes down. Right? And if we're building, I don't know, if we're building something, if you're in construction, you're building a house, you're doing work, that your energy is going into building the house, right? If you're studying your chemistry, you're doing your ALEX, your energy is going from you into, what you're learning, right? So it's by the system on the surroundings. So from the perspective of you, the sign is negative. You're losing energy. Now, sort of conversely, if your work is being done on the system by the surroundings, then the energy is increasing, right? So the sign is positive. So, let's think about this negative P delta V thing here, right? So work equals negative P delta V. We kind of explained, right, if you have the piston and the gas expands, and so you go from that's terrible. From that situation to this situation, right, so the volume increased. There's against a constant pressure. Then you're doing some work. But why is the sign negative here? Right? The pressure is constant. The pressure never changes. I mean, if you can do it with the pressure changing, but then instead of then you need to do calculus, right, which has to do with changes. So the pressure here is constant. What's a delta? Delta, we looked at delta very briefly at deltas a few slides back on Tuesday. We also looked at delta, did we? In some other context, right? So delta is the change, but it's always defined as the final state minus the initial state, right? That's the definition when we talk about delta. So another way we could write this is work equals negative P times the final volume minus the initial volume. So let's plug in some numbers, right? Let's say this is 10 liters and this is 2 liters, right? This is just so we can get the sign right. So if this is 2 liters, it expands to 10 liters. What's the final? The final is 10, and the initial is 2. Negative P times 8. Right, so P times 8 liters. And so the pressure is going to be whatever the pressure is. But the pressure is always going to be positive, right? In a situation like this, did I just mess that up? We're going to have negative, we're not going to have negative pressure, right? The pressure is going to be pushing down. It's going to be a positive pressure. And so let's just put in something like 1 atmosphere, okay? For P. When we do the math, we're going to get work equals negative 8 liters times atmospheres. Because of the negative sign. What does the negative sign mean in terms of work? Negative sign means that work is done by the system on the surroundings. When the gas expands, the gas is doing work. Work is being done by the system on the surroundings. So this negative sign is there to make sure that when gas expands, we know that work is being done by the system. Right? If that negative sign wasn't there, when this happened, what would we get? We would get a positive value. And what would it look like? It would look like work was being done on the system by the surroundings. Right? Here, what's happening? The piston is doing work. Right? Once it expands, it can do something. It can lift something up. So the system is doing work. So the sign has to be negative because energy is going from the system to the surroundings. So that's why this negative sign is here. So work equals negative P delta V. Right? When we look at thermodynamics, positive and negative are more of, we can think about them more of directions than, right? Positive is going, energy is going into the system, negative energy is going out of the system. Right? We can kind of think about them as more as directions than really kind of bigger and smaller, at least in certain contexts. So let's look at an example here. A sample of nitrogen gas expands in volume from 1.6 liters to 5.4 liters at constant temperature. What is the work done in joules? This is something we haven't really talked about yet. Right, but what is the work done if the gas expands against a vacuum or against a constant pressure of 3.7 atmospheres? So work we know is negative P delta V. If it's A against a vacuum, then what's the pressure? Pressure is 0, right? A vacuum means there is no pressure. So for A, it's the answer is kind of trivial. So delta V is, we can calculate delta V, but 0 times anything is 0, so it's going to be 0. Right, delta V is the volume of the final, 5.4 liters, minus the volume of the initial, 1.6. You get 3.8, and P equals 0. But P equals 0, so the answer is 0. For part B, if the gas expands against a constant pressure of 3.7 atmospheres, we get 5.4 minus 1.6 equals 3.8, again, and P equals 3.7 atmospheres. So negative P delta V is negative P is negative 3.7, and delta V is 3.8. And we do that math, and we get 14.1 liter atmospheres, or actually with significant figures, 14 liter atmospheres. But negative 14. Liter atmospheres is a unit of energy or work, but it's not a very it's not the standard unit, right? The standard unit of energy is going to be a unit called joules. Go ahead.
Wait, I still don't get this one. Why is the pressure in A 0? Is if you have a sample of nitrogen gas, can't you find the pressure from that?
It's an external pressure, right? It's the pressure from the outside. So it's like if you were doing this, I don't know, say in outer space, right? There's nothing pushing against it. If there's nothing pushing against it, it doesn't take any work to expand something, right? It only it's not work for me to go like this, right? It's work to go like this if you're pushing back against me, right? So because it's not the pressure in the container, it's the pressure that's pushing down against it. Okay, so the unit of liter atmospheres can be converted to the more typical, or the SI unit, joules, as follows. Right? 1 liter atmosphere equals 101.3 joules. And if you think back to your gas laws, does that number ring a bell somewhere? Do you remember your values of R? No? What? Yeah, sorry, go ahead. Not R. It's not the values of, the conversion factors between liters and kilopascals, right? Yeah, kilopascals. And so you use basically that same conversion to get between liter atmospheres and joules. And when you do it, you get the liter atmospheres and liter atmospheres cancel. What you're left with is joules, and you get negative 1430 joules. Very often when we look at data, and there's going to be data in the next few slides, I'm getting a little ahead of myself. Sometimes your answer, or sometimes the answer you're looking for, the information you're looking for, is in joules. Sometimes it's actually going to be in kilojoules. Right? And so when you're talking about joules, kilo means the same thing, right? 1,000 joules equals 1 kilojoule. Right. Ba, ba, ba. Okay. So the sign here is negative. Let's try to review this again, right? Because this is it's kind of can be hard for students to wrap their brains around. The system is doing work, right? The system is expanding against a pressure, so it's doing work. When the system is doing work, what does that mean? That means energy is going out of the system to the surroundings, right? The system is doing energy on the surroundings. The gas, in this case, is doing work on the piston that's pushing it down. And so therefore the sign is going to be negative. Right? That means the energy is leaving the system. So even though it's doing work, the sign is going to be negative. If work was being done on the system, that is, if we were pushing down and the volume were getting smaller, then what would happen? Then if it were getting smaller, then delta V would be negative, and negative times a negative is going to give you a positive, right? So then it would be positive. I want to go back just one second, just a little bit. Remember we talked about state functions, right? And we said things like volume or is a state function, temperature is a state function, energy is a state function. What is not a state function on this in this slide? Heat is not a state function, and volume is a state function, right? Because big, small doesn't matter on the path. Work is not a state function, right? So when you put heat and work together, you get delta E, right? But which is a state function. But between the initial delta E and the final delta E, Q can be big and W can be small, or Q can be small and W can be big, or they can both be medium. So those are part of the pathway, right, to get from one state of delta E to another state of delta E. So heat and work are not state functions. We're going to introduce another term here. This term is called enthalpy. Enthalpy is abbreviated H, and enthalpy is used to quantify the heat flow into or out of a system in a process that occurs at constant pressure. And enthalpy is kind of important, I guess, because I mean it's important, but it's important. Let's put it this way: one of the reasons why enthalpy is important is because a lot of the reactions that are done in chemistry, and a lot of the or say like chemical engineering or in a factory, a lot of them are done at, not all of them, a lot of them are done at constant pressure. What's the constant pressure? You know, when basically all of the experiments you do in Chem 109 in the lab are at constant pressure. And what's the constant pressure that they're done at? Mumble, mumble? Yeah, 762 or 1 atmosphere. They're open to the atmosphere, right? And if they're open to the atmosphere, the pressure that they're done at is atmospheric pressure, right? So 1 atmosphere. So much so that most of the time we don't even think about it, right? Everything we do, unless something strange is going on, pretty much is at constant pressure. So enthalpy is used to quantify heat flow in or out of a system when the pressure is constant. And enthalpy is, in fact, a state function. So we can think about the delta H equals the enthalpy of the products minus the enthalpy of the reactants. That is true, of course, because anything delta is final minus initial, and when you're doing a reaction, the final is the products and the initial is the reactants. But it's very, very hard to think about H. What is the heat of a bunch of chemicals, right? And what's the heat that are the products, and what's the heat of the bunch of chemicals that are the reactants? That's very, very hard to quantify. What's much easier to quantify is the change, right? The delta H. And so delta H is almost always what we'll be talking about, not H by itself. The delta H is a heat given off or absorbed during a reaction at constant pressure. And so we saw something like this before, right? In this case, the energy diagram. In this case, we're not looking at E or energy. What we're looking at is enthalpy. The two are quite related, but they're not the same. So as you go from here, you have H2O solid, ice. Right here, you have H2O liquid, water. In order to get from ice to liquid water, what has to happen? The ice needs to absorb some heat, right? And in Chem 2, you'll think about what's exactly happening to the heat and the molecules and so on. In this case, we just know because it makes sense to us. If you want to melt something, you need to add heat. Right? So heat is being absorbed by the system from the surroundings. And as long as you're not like in a pressure cooker or something, where as long as you're open to the atmosphere, the heat, the process occurs, the melting occurs at atmospheric pressure, at constant pressure. And so the heat absorbed is quantified by delta H, and it happens to have a value, 6.01 kilojoules per mole. The heat of the products is greater than the heat of the reactants. We can, in this case, we say delta H is greater than 0. The heat's going in. CH4 plus 2O2. CH4 is methane gas, right? So this is we talked about methane gas before. Methane gas is the gas that's used if you have gas heat. It's the gas that you use if you're on your stove. A lot of these buses now say this bus is powered by natural gas. It's CH4. And the CH4 burns in oxygen to give you carbon dioxide and water. We said whenever you burn something, right, whenever you have a reaction that gives off a lot of heat, the heat is going to the surroundings. And it's going from the system, which is the compounds, to the surroundings, which is the pot of water, or you, if it's the heat in your house, or to power the bus. So when heat is given off to the surroundings, right, it's coming out of the system to the surroundings, then the sign is going to be negative, right? Just like when we're thinking about delta E, if energy is going from the system to the surroundings, it's negative. And so you can see here, as you go from the reactants to the products, the delta H is negative. We say delta H is less than 0. And so enthalpy is this, it's a quantity that's kind of created because we basically live at constant pressure. Right? And so it makes it a lot easier to think about enthalpy because the pressure doesn't change. So remember this, right? E equals Q plus W. That was 2 or 3 slides ago. Q refers to the exchange of heat. So if you're at constant pressure, what is Q? Sorry? No. I just told you in the last slide. Delta H is the heat given off or absorbed during a reaction at constant pressure. Right? So if you're at constant pressure, Q is just delta H. And work, if you're at constant pressure and you're thinking about the expansion or contraction of gas, is negative P delta V. So we can change, or we can transform delta E equals Q plus W if we're at constant pressure to delta H plus negative P delta V, or delta H minus P delta V. So there's a relationship between delta E and delta H, right? And it's basically change in energy equals change in heat plus the change in work, or plus the work. So you notice that at constant pressure, heat becomes a state function and work becomes a state function. Right? It's when pressure is not constant that they're not. That they're generically Q and W. At constant pressure, Q becomes delta H and work becomes negative P delta V. What does that mean? P delta V, does that remind you of anything that you might have learned about, say, in the last chapter or so? PV equals nRT, right? That's, right, so here's the pressure, here's the increase in pressure, and that's the change, increase in volume. Here's a volume, here's an increase in volume. From here to here is a change in volume. There's different ways to get a change in volume. But if we also are at constant pressure, if we're also at constant temperature, so that means constant pressure and constant temperature, how do you get a change in volume? Right, so we have PV equals nRT, but we're not looking at PV exactly in that form. We're looking at negative P delta V. So the negative is easy, right? We can say equals negative nRT. But if P is constant and let's say we can hold T constant, how do you get a change in V? Right? P doesn't change, T doesn't change, R is a constant, so R doesn't change. Sorry? Somebody said something. Change in moles, right? So we can think about if P and T are constant, then P delta V equals delta N RT, right? Delta N RT. Where does this apply, or how could this apply? Right, so we can look at it this way also, delta E. So let's skip over this for now, and let's come back to it. Okay. Okay, let's look at, no, let's come back to this later, okay? Nope, 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 nope. Okay. Nope, nope, so, just kidding. Make sure you edit all that out, thanks. Okay, so, let's consider a reaction like this. Let's say we had, and this relates back to our gas laws, right? Let's say we had a reaction like this, as we've seen many times. N2 plus H2 gives us NH3. Right, and if we balance it, we get 3 and 2. And these are all gases. This is why it's important to put our states a lot of times. If this reaction were to occur in this vessel here, right, what would happen? Right, if you're put in your vessel, it's no longer a rigid, it's not a rigid vessel. Here you have N2 and you have H2, and it reacts to give you NH3. Let's say it all reacts, right? All of the N2 and all of the H2 reacts to give you NH3. There's no limiting reactants. You put them together so that they have exactly the right amount. What's going to happen to the moles of gas as you react N2 and 3H2 to give you 2NH3? Stay. Somebody's mumbling something that probably makes sense, but I can't really hear you. Okay. Would it help if I bribed you with candy? No? Okay. So, I have a bag full of Snickers in my office. I have 1 unit of N2 gas combining with 3 units of H2 gas. mole, kind of mole equivalents, right? How many total is that? 4. Those 4 units of gas are reacting to give me 2 units of gas. What happened to the moles of gas as I went from this side to this side? It decreased, right? It decreased, we can say, by, for each, as the reaction is written, by 2 moles. If I have a decrease in 2 moles, what does this tell me? That tells me I'm going to get a corresponding decrease in volume. Right? So that's what this is going to be good for. And we're going to, we're going to come back to that when we think about how to put together, when we think more about our P delta V. Okay. But in the slides, we have a break before we get there. Not a break in class. We have a kind of some more explanation before we get there. So we'll follow the slides. Okay, so delta H positive, negative, right? Delta H in this case we said was positive. In order to get from solid to liquid, in order to melt, you have to absorb heat, right? This is endothermic. Why is it endothermic? Because at constant pressure, delta H can replace Q, right? Q equals delta H if pressure is constant. And so heat goes into the system. And you'll notice that what's written here is not just kilojoules, which is a unit of energy, but it's kilojoules per mole, right? So what does that mean? That means for every 1 mole of ice, to melt 1 mole of ice, and if you wanted to, you could figure out how many grams that was. To melt 1 mole of ice, you need to put in 6.01 kilojoules of energy, right? 6.1 kilojoules are absorbed for every 1 mole of ice that melts at 0 degrees Celsius in 1 atmosphere. And so we did something kind of sneaky here, right? We applied these kind of we took these kind of abstract concepts of heat and so on. Now we're applying them to specific things that happen, right? Specific processes that are quite tangible, right? You need to absorb a certain amount of heat in order to melt your ice. Here's the way it's often going to be written, right? And so your book toward the end has a table of delta H's of reaction, or delta H's for all different kinds of processes. You don't have to, at this point, you don't have to memorize them. And this is how it's going to be written. You're going to have your reaction or the process that occurs, and the delta H per mole, right, that's associated with it. So 6.01 kilojoules per mole. If we were to reverse this process, if we were to go from liquid to solid, that is, if we were to freeze the water to give us ice, in order to freeze something, what do you have to do? You have to take heat out of it, right? You have to take, and so you take heat out of it by putting it in the freezer, right? When you put it in the freezer, the heat goes from the water basically into the freezer, right? And into the cold freezer. And so heat comes out of the system, goes to the surroundings. The sign would be negative, but the value would be the same. So the delta H for the reverse process for freezing would be negative 6.01 kilojoules per mole. Okay, and so here's the combustion reaction we saw, right? The combustion reaction, heat is given off by the system to the surroundings. Delta H is large and negative, right? System gives off heat. This is exothermic. Delta H is negative 0. It is less than 0. So another way to state this is 890.4 kilojoules are released for every 1 mole of methane that is burned or combusted at 25 degrees Celsius, 1 atmosphere. And again, if you see it tabulated in the back of your book or something, this is how it's going to look. You're going to have the reaction written out, and you're going to have the delta H kind of next to it or together with it. So let's think for a little bit. So if I want to boil my water, right? If I boil water, is that going to be exothermic or endothermic? It's going to be endothermic, right? If I boil water, the water has to absorb heat. So delta H is going to be positive or negative. Delta H is going to be positive, greater than 0, right? Okay. Okay, so this is starting to get where we're going, right? So the stoichiometric coefficients, when you write it out, always refer to the number of moles of a substance. Right, and so here, it's saying if we have 1 mole of CH4 plus 2 moles of O2, and we burn that, that's going to give us 890.4 kilojoules per mole. And so the per mole refers to what's written out here. And so that means, right, so we said that if the reverse the reaction, the sign changes, so liquid to solid is going to be negative 6.01. Now, if you have more than 1 mole, right, or less than 1 mole, you can, one way to think about it is multiplying both sides of the equation. And so if I go from H2O to solid to H2O liquid, in this context, it's saying 1 mole of solid to 1 mole of liquid is 6.01. Now, if we're saying now we have 2 moles of water, and we melt that 2 moles of water, solid, and get 2 moles of liquid, how much heat or how much energy do we need? 2 times 6.01 times, which is going to be 12. This is going to, well, let's put it this way. These points are going to be quite important because there are some reactions where it's quite difficult to measure the delta H directly, or there might be a reaction that hasn't been done yet, and you want to predict what the delta H or what the heat is, the energy is going to be. How much energy do I have to put in? And so we'll take these principles plus one that's about to come and be able to calculate what we don't know from what we know. Okay, so the states have to be specified. Okay. Okay, so right, the states have to be specified because solid to liquid is quite different from liquid to gas. Okay, so let's do a problem, right? How much heat is evolved if 266 grams of white phosphorus P4 burns in the air? Right, and so the equation, or the chemical equation, goes P4 plus 5O2 gives me P4O10. And the delta H is very large and negative, right? Because we're burning something, heat is going to be released, right? And so delta H is negative. So how can we do this? And remember a few slides back, or the slide before, we said the way this is written is for this reaction, right? 1 mole of P4, 5 moles of O2 gives me 1 mole of P4O10 and releases 3,013 kilojoules of heat. If I had 2 moles of P4 and 10 moles of O2, what would this be? It'd be double, right? So 6,026, negative 6,026. Oh wait, what do I need to do? I don't know how many moles of P4 I have, but I have some mass. Can I go from mass to moles? Yes, how do I do that? Molar mass. So yes, we need to remember how to do these things. So the molar mass of P4 is 123.9. I'm not going to calculate that because we know how to do that. And we do grams divided by grams per mole gives me moles, and that's going to give me moles of P4, right? This is going to cancel with this. And then I multiply that by the delta H kilojoules per mole, right? So 3,000 kilojoules per 1 mole. The moles and moles are going to cancel. Right, the grams and grams cancel, the moles and moles cancel, and I'm going to have kilojoules. So when I put that together, I'm going to get negative 6,470 kilojoules. How much heat is evolved, or how much heat is given off? When we're talking about how much heat is being given off, we would say 6,470 kilojoules is being given off. Right, the change in heat is negative 6,470. Okay, and let's take a break, as this is going to take a little bit. It's actually the same reaction that's written up there. The reaction written up there is thermochemistry. The delta H is given. So during the break, someone asked me, how do we know what these delta H's are? Right? Those delta H's are generally quantities that have been studied, and so you look them up. In the back of your book, there's going to be tables of delta H's for all sorts of different reactions. And so, right, and so that's the reaction that we're looking at. This is kind of and this point over here, right, the volumes of the liquid and the solid and the aqueous solutions. Anything that's not gas, this actually applies to this problem also, or to this discussion also. Anything that's not solid, liquid, or gas is going to be or anything that's not gas, right, that's solid, liquid, or aqueous solution. The volume of that is going to be very, very small relative compared to gas. And so when you think about the volume of anything that's not gas, we assume it's zero, right? We assume basically it doesn't count. And so when we do this reaction, when we do this reaction, have something like this, right? So what's going to happen? You have your piston, you have something that's already here, air and water vapor. That never changes, right? The air and the water vapor never changes. When you do the reaction, what does change, right? What changes is you get the evolution of some gas, H2 gas. When the H2 gas gets produced, if we think again about this, right, P delta V equals delta nRT, what happens to the volume? The volume is going to increase. Why is the volume going to increase? It's going to increase because you produced some gas, right? In this case, 1 mole of gas. So remember this, right? This is from, I don't know, 3 slides back or so. Delta E equals delta H minus P delta V. Delta E and delta H, we can think about how to interconvert between the two of them. Based on this, right, where P delta V equals delta nRT. Okay, so we can do this calculation, PV equals nRT, right? So at 25 degrees Celsius, 1 mole of H2 has a volume of 24.5 liters at 1 atmosphere.
Are all these like equations can be given to us in the exam?
No. So what is this equation? What is this equation here? This equation comes from delta E equals Q plus W, right? Q, we said, equals delta H if the pressure is constant. That's kind of by definition. And W equals negative P delta V, right? So we put those things together, we get delta E equals Q plus W, or delta equals delta H minus P delta V. So what does that mean? That means the difference between delta E and delta H is the work that's done, right? And what's the work done? The work done is negative P delta V. It depends on whether there's a change in volume. And what does the change in volume depend on? It depends on whether there's a change in moles of gas. So the delta N here is moles of gas, right? Because it's the gas law, right? So in that case, what's delta N up in this reaction up here? No, what's the value of delta N? The value of delta N is 1 mole final minus 0 moles initial, so it's 1. Right? In this case, we said delta N is, in this case, is actually going to be 2 moles final minus 4 moles initial. It's going to be negative 2. Right? The change is from 4 to 2. So in this case, let's erase this because we're not using it right now. Yeah.
On the exam, are you always going to give us delta H, or is it just for these type of questions you're going to do?
Well, you'll either be given delta H, or you'll be given the, or you'll be asked to find it. You'll be given enough information to figure it out. So delta E equals delta H minus P delta V. So in this case, what is delta E? Delta E equals, well, delta H is negative 367.5. And what's P delta V? Well, we're assuming that the pressure is 1 atmosphere, right? We're assuming that the apparatus is open to the air. And so P delta V is, or negative P delta V is negative 1 atmosphere times delta V, which is 24.5 liters. And we know that because 1 mole of H2, you can do PV equals nRT. You can use this equation. You're getting 1 mole is 24.5 liters, right? That's just a PV equals nRT problem. And so we get negative 24.5 liters atmospheres. But the problem here is that this is in what? This is in kilojoules. This is in what? Liters atmosphere. So do you remember the conversion between liter atmospheres and kilojoules? 101.3, right? So negative 24.5 liter, that's between, liters, atmospheres, and joules, right? So times 101.3 joules per liter atmosphere. And so that's going to give us I think it's, I don't have that. Um, negative 2583.15 joules. Right. We're still not really happy with this because we need to get to kilojoules, right? So, yeah. 2481. That sounds a little better. 2481.85. And so this is in joules. We're still not totally happy, right? Because we want to get to kilojoules. So if we convert from joules to kilojoules, and this is going to have three significant figures, right? So it's going to be negative 2.48 kilojoules, right? So we say 2480 joules, 1,000 joules per kilojoule. We're going to get negative 2.48 kilojoules. So it's going to be negative 367.5 minus 24.5 liters atmospheres, which is actually negative 2.48 kilojoules. And when we put that together, what we're going to get is negative 370.0 kilojoules, right? 369.98 or 370.0 because it's decimal places, right? Kilojoules. Actually, it's going to be kilojoules per mole, right? Kilojoules per mole and kilojoules per mole. This is really liter atmospheres per mole because it's per 1 mole of reaction. Yeah, they're subtracting, right? So it's. And so what do we notice? We notice that the delta H is negative 367.5. The delta E is negative 370.0. And the work is negative 2.5. The work is actually quite small relative to the delta H, and that's pretty typical. Okay, so here's another thing that I mentioned when we talked about enthalpy. When we started talking about enthalpy, we said it's very hard to measure what H is, right? What is the value of H of an object? But it's much easier in general to measure delta H. In some cases, it's still delta H is something that we still can't kind of get at directly. Sometimes we can use we can use indirect means to find delta H. So one of the things that we can use is the standard enthalpy of formation. Standard, under standard conditions, is delta. We're going to use this little superscript 0-ish kind of thing. Standard enthalpy of formation as a reference point. We'll see what that means shortly. But before we talk about that, when we're talking about thermochemistry, standard is 1 atmosphere and 25 degrees Celsius. And I'm convinced that they do that just to confuse you because for gases it's 1 atmosphere and 0 degrees Celsius, or 298 Kelvin, or 273 Kelvin, right? And it's because two different groups of scientists, one was working on gases, one was working on thermodynamics, and at some point, they were independent of each other. One decided to work at 25, one decided to work at 0. So here's the reference. So what is this? So what is the standard enthalpy of formation? The standard enthalpy of formation is the heat change that results when 1 mole of a compound is formed from its elements at 1 atmosphere. So this enthalpy of formation has to do with forming a compound or forming a molecule from the elements that it's made up of. So if I was thinking about water, I was thinking about, say, liquid water. How could I think about its formation from its elements? Well, what elements make up water? Hydrogen and oxygen. So I need to know something about hydrogen and oxygen. I know it's not H plus O, right, because hydrogen doesn't like to exist as H, it likes to exist as H2. And oxygen doesn't exist at O, it likes to exist at O2, as O2. And I know that at 25 degrees Celsius, that is room temperature in 1 atmosphere, hydrogen and oxygen are in what state? Yeah, they're gases. So hydrogen gas plus oxygen gas. And I know this isn't complete because it's not balanced. So how do I balance this? Say it again? 2H2 and 2H2O. That's true, right? That's good for balancing equations on your exam and so on, except it's talking about 1 mole of the compound. Here I got 2 moles of the compound. So what do I have to do? I have to divide everything by half. So instead of 2, 1, and 2, I'm going to write it 1, 1/2, and 1. Right? So 1H2 plus 1/2 O2 gives me 1H2O. So this would be the equation for the formation of liquid water. And if I looked that up on my table of enthalpies, the enthalpy that I get would be the enthalpy of formation. What about if I'm thinking about, let's say, H2 gas? What's the enthalpy of formation of that? Sorry? Or what's the equation of formation for that? All right, that's kind of a quick trick question. This is the element in its most favored state, right? So if we really wanted to look at it, it would be like H2 gas gives us H2 gas. There's no change. Delta H HF for formation equals 0. And actually the enthalpy of formation, standard enthalpy of formation of any elements in its most stable form is always going to be 0. So a lot of times we need to draw on some of the knowledge we know from like the first couple of chapters. We know that things like H2, O2, N2 like to be gases, right? We know that helium, neon, the noble gases like to be gases, like that metals except for mercury like to be solid at room temperature, that kind of thing. Okay, so now we understand what this, so what does this mean? Step back. So now we kind of know what we're talking about when we're talking about a formation reaction. The standard enthalpy of formation is the enthalpy associated with this process. How can we use this in a way that's useful? Right. So here we have, well, before we talk about that, here's some examples, right? So O2 gas is the most stable form at 25 degrees Celsius. Carbon. Carbon has lots of different forms, right? One of them is graphite. That's the so-called lead in your pencil. That's the most stable form. But each of these also have some other forms that are not too unstable. That means that they actually exist. So O3 is a molecule called ozone Right, this is the ozone that's in the ozone layer. That's the ozone that some people have kind of gives people respiratory problems. O3 is not the most stable form of oxygen at 25 degrees in 1 atmosphere. And so therefore its delta, it actually is going to have a delta HF. That's not 0. Right, diamond is not actually the most stable form of carbon. And so it will have a delta HF that's also not 0, whereas the graphite is going to be 0. So how can, okay, so yeah, here's some examples, right, that's table in your book. You can look them up. And that's what we said already. So let's think about, no, it's not what we said. Standard enthalpy of reaction, delta H naught, not formation. This is for any reaction, can be defined as follows, right? We have A plus B gives us C plus D, right? Where the big A and the big B and the big C and the big D, those are particular reactants and products, right? And the little a, the little b, the little c, and the little d, those are the coefficients, right? This is going to have, like any other reaction, and like any reaction, it's going to have a delta H associated with it. We can find the delta H associated with this reaction from the delta HFs, the delta H of formations of the products, and the delta H of formation of the reactants. Now, this equation looks kind of big and scary, but it's really not. What's that? It is a new language, and it's a new language, and that's why it looks scary. But once you understand it, it's not scary at all. Well, first of all, let's say what's this. Let's figure out what this is saying in English. Does anyone know or remember from math what that sign is? It's sigma, and it stands for the sum, right? And so this is basically saying it's the sum of a whole bunch of stuff, right? So the delta H of the reaction equals the sum of delta HF naught for all the products minus the sum of delta HF naught of formation for all the reactants. That's a little less scary, right? And if we can look up the delta HF for A and for B and for C and for D, then I can just add up the delta HFs for C and D, the products, and add up the delta HFs for A and B, the reactants, and subtract them.
What does that stand for RX?
The reaction, right? So the delta H of this, whoa, of this whole reaction can be defined as the delta H's of this minus this. So in a way, you don't even have to write this down, right? You don't even have to remember this if you remember this, right? This is English, and it's, looks a lot less scary. What the m and the small m and the small n mean is we have to take into account the coefficients. So if it's 2a, then we have to take the delta HF for A and multiply it by 2. If it's 3b, we need to take the delta HF for B and multiply it by 3. So here's the question. What is the enthalpy change associated with H2 plus 1/2 O2 gives me H2O? Well, what's the delta HF of H2? Gas. 0, because I just told you that, right? And because it's an element in its most stable state at room temperature, what's the delta HF for O2 gas? Also 0. So all I need to do is look up now the delta HF for H2O. And if I go back and look at this table over here, you can't really see it very well, but either the table will be given to you or the values will be given to you, right? You don't have to memorize these. It's going to be negative 285.8 kilojoules per mole. Right, so when we do this, whoops. And so when we do this, we're going to say the sum of the delta HF for all the products, which is, what did I say it was, negative 285.5. This is for the sum of the delta HF, not for the products, minus the sum of the delta HF not for the reactants, which is 0. And so negative 285.5 minus 0 equals negative 285.5 kilojoules per mole. Not too bad, right? What about the second one? So I need to know NO2 and N2O4. And if I look those up, NO2 is here, right? NO2 is 33.85. Is that positive? Yeah. Is 33.85. And N2O4 is 9.66. And these are all in kilojoules per mole. So delta HF, not values for so, and the reaction is 2NO2 reacts to N2O4. Yeah, okay. So what's the calculation? The calculation is delta H naught of the whole reaction equals delta H naught, the sum of the products, right? So it's going to be 1 times N2O4, which is 9.66, minus the sum of the reactants. Now in this case, what's the sum of the reactants? It's 2 times 33.85 because of this 2 here, minus 2 times 33.85. And so it's going to be 9.66 minus 67.70, right? 67.70. And that's going to give me negative 58.04. And that's still in kilojoules. These are in kilojoules, all in kilojoules per mole. It's still going to be kilojoules per mole. Okay, so is this reaction endothermic or exothermic? Exothermic. Does it give off heat or does it or absorb heat? It gives it off. Very good. Sorry? Say it one more time. I'm not. I don't like to judge people, but VJ doesn't really seem like a Jewish name to me. What did you say? Passover? No. Oh, Passover. I said okay. I thought you. Okay, you can edit that out too. Okay, so that was just to check if you're awake or not. So that's an example of Hess's law. Right? Hess's law says when reactants are converted to products, or when you have some reactions, you have a reaction. The change in enthalpy is the same whether the reaction takes place in one steps or a series of steps. Right? And why is that? That's because enthalpy is a state function. Right? So that means it doesn't matter how you got from here to there. All that matters is that you got from here to there. And so, in other words, it doesn't matter how we got from, if it's A to B, if it doesn't matter if we go from A to B directly or if we go from A to C to D to E and then to B. So what is this really doing, right? If we look at this reaction here, the NO2 reaction, this is saying, okay, we're going to go from NO2 back to the elements, right? That's what delta HF tells us. It tells us the enthalpy for the formation of NO2 from the elements. So we're going to go from NO2 back to nitrogen and oxygen. And then we're going to go from that nitrogen and oxygen over to the N2O4. Right? That's really what this reaction, this thing here is saying. And so that's an example of Hess's law. Now, Hess's law can be, this is not the only application of Hess's law. Right? So Hess's law basically says, because enthalpy is a state function, the delta H is going to be, I'm going to be able to calculate, I can't calculate the delta H directly, then I can calculate the delta H in steps based on what I already know. And because my computer's about to die, I'm going to give you an example on the board. And the example on the board, I'm not going to use real chemicals. I'm just going to use, so A's and B's and so on. So if I have A plus B gives me C, right? I want to find the delta H of that reaction. And I don't know what it is. But if I do know A plus D gives me E, and E plus B gives me D plus C, and I know the delta H for this one. I can add these two reactions together. If I add these two reactions together, what am I going to get? I'm going to get, on this side, A plus D plus E plus B gives me E plus D plus C. But, very similar to what we did when we looked at ionic reactions, if you have the same thing on the left and on the right, they can cancel. Right? So D and D go away, and E go away. What do I have? A plus B gives me C. When I add the two reactions, because enthalpy is a state function, I also can add the delta H's. Right? So when I add the delta H's, I get negative 34 plus 14. The delta H of the overall reaction, or the added reaction, equals negative 34 plus 14 equals negative 20 kilojoules per mole. So Hess's law, when we do Hess's law problems, we're going to look basically at 3 different rules. 2 of them we already looked at, right? One of them says if I multiply a reaction by a number, the delta H multiplies by the same number. So if I get A plus B gives me C, if the delta H here is negative 20, then 2A plus 2B gives me 2C. Right? I multiplied the whole thing by 2. What's the delta H of that going to be? 2 times negative 20, which is going to be negative 40. Right. The second rule, or the second thing, is going to says if the reaction is reversed, what happens to the delta H? The sign changes. Delta H naught sign changes. So if I go backwards from C to C gives me A plus B, delta H naught equals negative of negative 20 equals positive 20 kilojoules per mole. And the third one says, we applied it here without really even talking about it, is that if reactions are added together, the delta H naughts also add. So if I have A plus B gives me C, and that delta H is negative 20 kilojoules per mole, and I get C plus D gives me E, and delta H of that is negative 30 kilojoules per mole. When I add them, what am I going to get? I'm going to get A plus B plus C plus D gives me C plus E. Right, the C's are going to cancel. A plus B plus D gives me E. The delta H is going to be negative 20 plus negative 30 equals negative 50 kilojoules per mole. Okay, so I guess we'll, you're all getting restless. We'll let you out a few minutes early. But when we get back, we'll do some real problems that are associated with Hess's law. Right? So far, we're just looking at A's and B's and C's because it's faster to write down. But we'll eventually start looking at real reactions as well. When you get back, from spring break on Tuesday, we'll do our recitation, and so bring your worksheet. I'll send you an email reminder over the break.